everybody. So it is a pleasure to have Professor Jyotishman Bhowmick from Indian Statistical Institute in this weekly webinar, and he will be talking on the metric-compatible connections in non-commutative geometry. Jyotishman.
Okay, thank you. So I hope all of you can hear me well. So this is based on joint work with a lot of people. Devashish Koshyami, Shomarlo Joadda, Giovanni Landi, and my PhD student Shubhatam Mukhopadhyay. So right. So we will try to generalize something from differential geometry. So we will first need to recall or recapitulate the notions in the classical setup, and then we will state the problem and then try to solve it. So right. So and in the beginning, I should say that this talk will be completely algebraic, though the objects appearing in the lecture actually come from some well-known and well-studied Caesar algebras, but we won't be having any analysis in the talk. Right. So let's see. So so this is the classical situation. I will explain some terms and then state the problem. So suppose M is a smooth manifold, and for a natural number k, I will let omega km denote the space of k forms. So what does it mean? So it means that omega km is so the objects look like this. So any object in omega km, which is also known as the space of k forms, is a linear combination of things like this. Okay. So here D is the differential. So in particular, so if G1 is a smooth function on M, so then DG1 is a smooth form. And for natural number k, omega km, or in other words, the space of k forms is the span of elements like this. So yeah, right. So these f, G1, G2, Gk are smooth functions on the manifold M. Right. So in particular, so what do we have? So for if I take k is equal to 0, then I only have f. So these terms don't appear. These terms. So it's actually equal to the algebra of the smooth functions on the manifold M. So if k is equal to 1, then the omega 1 m, this is the space of 1 forms. So where the elements times dg, where f and g belongs to simply m. So this omega 1 m is going to play, or its non-commutative analogs are going to play a very important role in the lecture. So let's remind ourselves how they look like, at least in a classical situation. And so if the dimension of the manifold is let's say d minus 1, then omega dm is 0. Okay. So right. So let's again look at this expression. So if suppose h is a smooth function on the manifold, then I can multiply this expression by h on the left. But then the, the, the definition of omega km says that after multiplication, the element still lives in the space of k form. So omega km is a left module. Okay. But C infinity m is a commutative ring. So any left C infinity m module is also a right C infinity m module. So simply, if you, so just define the right action by action. So suppose E belongs to omega km and A is a smooth function. I know I want to define E dot A. So you directly define it as A dot E, and it's a right module is defined by this dot. And most importantly, the left action by infinity m and the right action by. In other words, so this omega km is a C infinity m bimodule. So a bimodule action and the right action is commute. We will need this that's defined to be all the, so the direct sum of all these guys. So since each of this is a infinity m bimodule, so the direct sum is also so. Okay. Okay. So what do we get? So if we sort of summarize what we saw here, then we get the following. So we have a data omega dot m, wedge, and d, where d is the Dirac differential, omega dot m is the direct sum of all the k forms, and wedge is the usual wedge product. So we have this. So omega dot m is a direct sum of this, with the zero forms is just the algebra C infinity m. Okay. So then let's get to the wedge. So wedge is a C infinity m bimodule map, meaning that is there any question? Hello? Can you hear me?
Yes, I can hear you. But
is there any question?
Is there any question?
Okay, no. Okay, so I think I can continue. So right. So so this is the usual wedge product. So it's defined on this guy, and it's well, actually, so this wedge makes this omega dot m into an algebra, and it has the property that if you apply wedge on a J form and a K form, it will um, map it to a J plus K form. Okay. Okay. So now we get to this D. So D is the usual Dirac differential. So it satisfies this property that D square is equal to 0. So D takes a guy from D acts on a J form and maps it to a J plus 1 form, and the compatibility between D and wedge is given by this formula. Okay. Okay. So And also I should mention that this we have seen this that this the bimodule of J forms, that is omega Jm, is the span of these guys. So from here I am introducing a new convention. So in the last slide I wrote the functions on the left, but from now on I will start to write the functions on the right. So here, this aj plus 1 is a smooth function, and it has appeared in the right. But by the definition of the right action, so this guy is actually aj plus 1 dA1 wedge, sorry, this should be dA2 wedge dAj. Okay. So, yeah, I mean, mm, uh, here, of course, it doesn't matter whether I write a function like this on the left or on the right, but whenever I go to a differential calculus over a possible non-commutative algebra, so writing things on the left and the right matters, because the actions on the left and the right are different. Okay. Uh, so right, and here is another notation which we will use again and again. So I will denote this the bimodule of one forms by the symbol E. Okay, and yeah, I mean it's well known that it's a finitely generated projective right to infinity module. Of course, it's also a finitely generated and projective as a left to infinity module. But I will, yeah, I will basically use this convention. Okay. So what do we have? So I have a bunch of bimodules omega Jm, which looks like these. I have a wedge map which maps a J form tensor a K form to a J plus K form. And I have this Theorem differential whose square equal to 0, and it acts on the wedge product of omega and eta by this formula. Okay. So a moment's reflection will yield that this data well, I mean, so the main input has been this algebra. Okay, so this is a commutative algebra, and everything is defined in terms of these. So this is a Synchronity bimodule, and I have some maps called wedge and D, which satisfy certain properties. Okay, so so the way that this whole thing is written up, if I replace the algebra Synchronity M by any non-commutative algebra A, this whole thing, the whole definition will make sense. Okay. So there is no reason why I can't replace this. I mean, consider this same data by.
Jyotishman, sorry to interrupt you. I think Professor Ajit Iqbal Singh has some question.
Yeah. Yeah. Yes, please.
Line 2 from below.
Yeah. Yeah. There is a typo. So this.
Okay. Good.
DA1 should be DA2.
Yes. Thank you.
Yeah. Because otherwise it's 0, right? So right. So right. So it makes sense to consider this data, and we will replace this algebra by any non-commutative algebra. Okay, so what's that? So I will fix a non-commutative algebra A. So it will have a unit, and then I will say I'm going to define what a differential calculus will mean. So right, so of course from now now this what I'm going to define won't have anything to do with any manifold, but the thing
Jyotishman, Ray has some question for you.
okay, yeah, sure.
My question is actually, so you have the way you have put differential form in the last slide. So if suppose we have, I mean, if you have a D operation and this way operation, everything abstractly, the way you are saying that you can make it, maybe you can put it abstractly, then can you guarantee that it will be the differential form? So is there any?
I'm sorry. So this is what my definition is going to be. So what's your question?
I mean, so that it will characterize the differential form. I mean, so if you have a to be C infinity m, and then you can say that these properties, they will characterize the differential form.
What do you mean by that? Of course, I mean, so there is a very uh, sophisticated machinery by which recover some smooth functions from spectral data, but I am not uh, talking about that.
Okay.
So, but yeah, so this is much more uh, general, and of course, I mean, so here, I mean, so my input data includes these guys. So there is no question of recovering it, and also what I'm going to state. So here also my input data will have these waveforms. Yeah. So I fix up a non-commutative algebra A, and I consider this data where this guy is an A bimodule. It's a direct sum of these constituent bimodules, and I define the omega 0A to be A. I am going to call these omega JA as the space of J forms. So omega 1A I will will be called the space of 1 forms. I postulate that I have an AA bimodule map which maps a J form tensor K form to a J plus K form. I postulate the existence of a map which has the properties as before. I say that the J forms are spanned by this. Of course, I mean, so again, there is a data here. I mean, there is a typo here. And finally, I also will demand that E, which is the space of 1 forms, has to be a finitely generated projective writer module. So I need this assumption because in the absence of this, there will be no connections, and connections are something which we are going to study. Okay. So I again, as before, I have a bunch of A bimodules omega JA. I have a wedge map and a map like the Jiram differential, which satisfies the properties as before. Okay. So this is my setup, and in what follows, it will be often helpful to define everything in this extended setup because then the classical definition is included within it. Okay. So I'm going to define what connections are. So whenever I talk about connections, I will fix differential calculus over an algebra A. This algebra A is not might not be uh, uh, commutative, but yeah. So I will, as before, I will denote the space of one forms omega 1a by the symbol E. Okay. Okay. So suppose I have an A bimodule F. So it is a left A module as well as a right A module such that the left and the right actions commute. So I will consider what are known as right connections. So, it will be a complex linear map from F to F tensor E, but the tensor product is over A, such that for all F in F and A in A, this Leibniz-like condition is satisfied. So in the classical picture, omega 1, when A is equal to C infinity M, then omega 1A or E will stand for the space of sections of the cotangent bundle, and F will stand for a vector bundle over a manifold M. And then we get back what we know from differential geometry. In the classical case, left connections and right connections are in one-to-one correspondence, but in the non-commutative case, that's not the case. So just remember that if you apply the connection, so then the E applies on the right, and then the formula in the Leibniz formula, I only know what happens when you apply nabla to F times A. I do not know what happens when you apply nabla to A times F. Okay, so that's a right connection. Okay, so and in particular, if you take F to be E, then this guy is a map from E to the is a map from the space of one form to the space of two forms. Why? Because as I said, so D is a map from the one forms to the two forms, and E is taken to be omega 1A. So D applied on E takes us here. And okay, so let's apply this on E. This nabla takes E to E tensor E, because I have taken F to be E. And this map wedge maps E tensor E to omega 2A. So this guy makes sense. This can be checked to be a right A linear map, and I say that nabla is called torsionless if this guy is equal to 0. So and it can be easily checked that this definition coincides with the classical with the classical definition of torsion when A is equal to say infinity M. So with the definition of torsion, there is no problems. It easily generalizes to the non-commutative situation. So okay, yeah. So now we get to metrics and connections. So again, our input data is differential calculus, and I have fixed an algebra A. So I will need to state what a metric is. So I will here I am working with the general non-commutative setup. So I will fix this some map sigma from E tensor E to E tensor E. Remember that sigma stands for the space of one forms. and this is the analog of the flip map. So a pseudo-Riemannian sigma metric on E. So what I'm going to define depends on this choice of sigma, is a map from E tensor over E over A to A. It is right A linear, such that G has the G is compatible with sigma in this sense. So classically, it says that if you apply G on E tensor F, then that's the same as applying G on F tensor E. So it's symmetric. So this is the generalized symmetry, and I will have this particular non-degeneracy condition. So in what I am going to do, so the positive definiteness of the metric won't play any part, and so I am not going to demand any positive definiteness of the metric. Okay. Okay. So thus what I have defined depends on this choice. Let's see. So here are some remarks. In the non-commutative case, there is no unique choice of sigma. So when A is equal to C infinity M, and I am working with the classical differential calculus, then this is just a flip map. So flip meaning that if you if it acts on E tensor F, it just gives F tensor. The main point to remember is that when A is a non-commutative algebra, and I have some A bimodule E, so then the flip map is not defined at this level. I mean, it's usually not well defined, and that's one of the key problems. Okay. Okay. So a metric is a map from E tensor E to A, and this depends on the choice of a sigma. So that's the lesson. Before the next slide. So so suppose you have a differential calculus and you have a connection and you have a metric. So you want to say what the how the metric is related with the I mean, so I mean, you want to check if the connection is compatible with the metric. So that's what the metric compatibility condition is. So I have a manifold M and the usual differential calculus, and I have fixed a metric G. So recall that it's a right and linear map from here to here. Okay. So I will fix a connection and then say when that connection is compatible with the metric G. So suppose I am given this connection, so I say that this nabla is compatible with G if this happens. So you take two elements E and F from the algebra C infinity M. You apply D of G E tensor F. So G takes value in C infinity M, which is the space of 0 forms, and then you apply D. It lands in the space of 1 forms, and here again you can easily check that this is a guy which lands in the 1 forms. So this is an equality of 1 forms. So and yeah, so this is some equation, but what we need to remember is that it's kind of non-trivial to extend this this definition in the non-commutative situation, because so suppose I start from E tensor F. So then let's see what it does. So I first have A, E, and then F. So here I first have E and then F, but here the order is reversed. So implicitly I have applied a flip map here, okay? And then, and here it's obviously I have used a flip. So there are two flips appearing in this definition, and as we saw in the last slide, the flip map is not usually well defined if the bimodule is over a non-commutative ring. So for the major part of the talk, so we will try to generalize this equation. So what good is it? So it's needed and it's useful because of the following theorem. So suppose M is a manifold, and I have fixed a pseudo-Riemannian metric on it. So then there exists a unique connection which is torsionless and compatible with G. So it's a unique connection. We have seen what the torsionless means, and in the previous slide we saw what the compatibility means. This nabla is called the Levi-Civita connection for the metric G. Of course, if you change the metric G, you will have a different connection. And it's important because whenever we say so the different types of curvature of the manifold, it's the curvature of this particular connection. Okay, so it's an important object. So we are interested in non-commutative differential calculus over a possibly non-commutative algebra. So suppose I have a pseudo-Riemannian metric on the space of one form. Then I can ask the same question: that does there exist a connection which is torsionless as well as compatible? So then I need to make sense of both torsionless and compatible, right? So we already saw what torsionless means even in the non-commutative situation, and in the in the previous slide we saw that it's difficult to, well, at least it's not straightforward to make sense of the metric compatibility condition. So yeah, so that is going to be our goal when I have a differential calculus over a possibly non-commutative algebra. So yeah, so this is the question. So let's see how far we could go. So I will just mention some results. So I won't bore you with the gory details. So we have had a bit of some success. So we looked at, well, of course, it's clear that just to make sense of the metric compatibility condition needs some assumptions. Okay, so many people have worked in this area. So I will just mention 3 words. So here we applied some condition on the differential calculus, and we worked with the metrics which are both left alinear and right alinear, and we saw that we have a unique connection. So now it makes sense to compute curvatures with respect to the Levi-Civita connection. So this was extended to metrics which are not necessarily bilinear. It's a smaller class. Uh, and yeah, so I mentioned that in order to define a metric, you will need an analog of a flip map. So if you start with the same differential calculus, then automatically you have some a flip map. So in this setup, we also had the theorem just to show that uh, uh, that there are indeed some interesting examples. I will show the next slide. So this fuzzy sphere, the quantum Heisenberg manifold, and some peripheral deformations. And Joadda had this example of spectral triple on the Kunz algebra. So all these examples come from some natural spectral triples on some algebras. And in a different direction, so if you work with some Hopf algebras, and if you take consider bicovariant differential calculus, or in other words, some differential modules, then you can uh, apply, demand some conditions which will ensure the existence of this connection for any bi-invariant. And you will see that, and we saw that if the metric satisfies an invariance property with respect to the Hopf algebra action, then the connection also has the same property. So yeah, so these are just glimpses to some results. Right. So now I mean, I don't want to explain everything here, just to show that I mean, it makes sense to generalize, and some results that we have got. So we will only concentrate on the question of defining metric compatibility of a connection for non-commutative differential calculus. We already saw one definition, and we saw that it involves two flips, so it's kind of difficult. So I will now state a classical theorem, I mean, which is very easy and well known, which will help us to define metric compatibility in the non-commutative situation. So this is the classical case. So I have a pseudo-Riemannian manifold. So and I will define and I will denote the special one forms by the symbol E. So remember that G is an element on E tensor E is a right A-linear map from E tensor E to A. Okay. Okay. So I am going to define. I'm going to state a theorem which gives an alternative definition of metric compatibility. Okay. So these are several steps. So suppose I have essentially a vector bundle over M. It then makes sense to talk about connections. Suppose I start with a connection on this vector bundle. Okay. So then it can be easily checked that that from nabla I can canonically induce a connection on this guy. Okay. So I will denote this connection by nabla F tensor F. Also, if you have a connection on the vector bundle F, then you can define a vector bundle. You can define a connection on this bimodule. Okay. So call this nabla F star. Okay. So now let's take E to be omega 1 M, and suppose I will take F to be E. So suppose I am given a connection on E. So from here, I get a connection on E tensor E, and here, if I choose F to be E tensor E, then I get a then part 2 gives a connection on E tensor E star. Okay, so I repeat, I start with a connection on F is equal to E. From the first part, I get a connection on E tensor E, and then I take F to be E tensor E. So from part 2, I get a connection on E tensor E star. Yeah, so E tensor E star is just this guy. Now, G belongs here, right? So it makes sense to apply nabla E tensor E whole star to G, right? And then it's a theorem that nabla is compatible with G if and only if this is equal to 0. So this is that nabla is so is G parallel, right? So so this is the definition we are going to use. Okay, so remind ourselves that there are 2 steps. From a connection on E, I got to a connection on E tensor E, and then tensor E, I got a connection on E tensor E whole star. And then this guy makes sense, and then it makes sense to say that equal to 0. And if nabla satisfies this equation, then it's a theorem that nabla, so this holds if and only nabla is compatible with G. Okay. Okay, so let's explain the idea. So suppose we have a differential calculus over an algebra A. So suppose this is a differential calculus, and nabla is a connection such that nabla, this connection on E, induces a connection on this bimodule. Then it makes to define to say that nabla is compatible with G if this is satisfied. Okay, so thus this definition coincides with the classical definition. E is one forms over a manifold M. Okay, so just a mark. I said here that suppose it's a differential calculus and nabla is a condition that nabla induced, right? So from just this part, it's apparent that this, so I can get a connection here if my my differential calculus satisfies properties, or can satisfy some properties, or if there is a restriction on both the differential calculus and connection, right? So once again, so I mean, if you start working with this problem, it gets clear that you can proceed only if you have some assumptions on your data. So there are 2 ways to go about it. So one, you can either impose some restrictions on the differential calculus. 2, you can impose some restrictions on the connection, and 3, impose some restrictions on both of them. Okay, so so this is our goal. So if you have a connection, I will try a connection here. because once I do this, I can make sense of nabla G is equal to 0, and then I can at least make sense of the metric compatibility condition. So I will give you two methods to it. In the first method, so it's after Beggs and Majid. So they work with any differential calculus, but they work with a specific class of functions. Okay. So we will need this definition. So I have a differential calculus, and this suppose I fix such a bilinear map. So as you will recall, so I will need this map for defining a metric of, and of course the choice is not unique. So a right is called a right bimodal if in it has this property. So for a right connection, I know a formula for nabla of EA. But if I have a bimodal connection, in addition to EA, I can also say something about AE. So it's given by this. Of course, any bimodal connection is a connection, but not all connections are bimodal connections. So you, if you only consider bimodal connections, so then you are applying some restriction on the class of connections. So and note that bimodal connection, yeah, it depends on the class of bimodal connections on E depends on the choice of the sigma, because sigma is applicable. Classically, there is no difference between connections or by and bimodal connections, but since in the non-commutative case the sigma is not a flip, so the classes are different. Okay, so it's so Beggs and Majid showed that if you have any differential calculus, and if you fix this sigma, and if you start with a connection on E, then you can extend this connection to E tensor E by this formula. So so here you have made this made use of this sigma. Okay, so let's recall. So so we have two steps to make sense of this nabla G is equal to 0. The first step is to extend a connection from E to E tensor E, and in the next step we I need to extend from a connection on E tensor E, I need to define a connection on the dual or the home space. So this proposition by Beggs and Majid does the first step, and this requires a restriction on the connection. Okay, so now what I'm going to say works for any differential calculus and any connection. So this is a general fact that if you have a projective right A module, so there exists this upper E1 into En in E and lower E1 into En E, such that this thing holds, these equations hold. So yeah, so these are some reconstruction formula. So we will make use of this formula to do this. You have any by module E, and you have any right connection on E, then one can define a connection on this E star. E star is just this dual space by this formula. Okay, so it doesn't need the existence of the sigma, and it works for any connections. So in other words, so if you have a bimodule F, then you have this recipe gives you a connection on F star from a connection nabla on F. Okay. So this E is just the evaluation map. So from E star tensor E, and it takes value in the algebra. Okay. So this is the second step. So I need to tell you what a left connection is. So So the only difference is that what you get here is a left connection. So instead of E star tensor E, you have an object in E tensor E star. Okay, and left connection is it's almost the same thing. It's just says what AF is, and so here F appears on the right instead of on the left, and I have this thing. So what's the difference with right connections? So a right connection takes value in F tensor. A left connection takes value in E tensor. Okay? For a right connection, I only know what happens if you apply nabla to FA. For a left connection, I know what happens if you apply nabla to AF. Okay, this is just a side remark. It can be checked that it's the independent choice of these guys, and thus, if you work with bimodule connections, so now you know how to make sense of this. So start with a connection on E, you get a connection on E tensor E that requires bimodule connections, and in the second step, yeah, it was free. So this is the first method by Beggs and Majid, where we impose some restriction on the set of connections. So in the next approach, we will apply some restriction on the differential calculus, but we will work with any connection. So suppose I have a module. Like the classical case, the left action and the right action can be different. So it makes sense to look at this guy. This Z of E is the center of E. And it's clear why it's called the center. So if you on the left, you can immediately switch it to the right. So we will make an assumption on the differential calculus. So suppose ED is a differential calculus such that this multiplication map is a vector space algorithm. Okay. So it takes value from the center tensor A. It's over the center of A. Makes sense because the center of E is a bimodule over the center of A. You simply multiply, and then you postulate that this is a vector space algorithm. Suppose my differential calculus is such that the space of one forms has this property. So then it's clear that the right A linear span of the center is the full E, and also as a bonus by a theorem by sorry, I just forget his name, but it's known that there exists a unique bimodule map such that if omega and eta are centers, then the action of sigma on omega tensor eta is just the plane. Of course, I mean, if omega and eta are arbitrary elements, it's almost never possible that the action on sigma is is the flip on the whole of the center, but this sigma has this property. So this follows from this property and is and was well known from the literature. So in the classical case, just in the first slide I remarked that in the classical case the left action is the same as the right action, so that when the z of e is the full of e, and it's clear that UE is an isomorphism, and there a sigma is just a flip map. Okay. So yeah. Okay. So here we start. So I start with differential calculus such that the bimodule of one forms satisfies this condition one. This multiplication map is a vector space isomorphism. So then I fix a connection on E. I want to define a connection on E tensor. I will do this in two steps. I will first define a map on a center tensor, the center. Okay, and it will take the value in E tensor E, as it should. Of course, this is not going to be a connection, but and in to define this, I will use this definition. So here we make use of this sigma, which on the central elements acts like the flip, and this is indeed well defined. Okay, so I have something here. Of course, this guy sits inside E tensor E. I want to extend it to a map on E tensor E. So I will need another recipe which will follow from our assumption. So suppose, so you look at this map. So whatever it says, so in layman's terms, it says the following. So suppose you take an element omega from here, eta from here, and a from here. Then this guy will map omega tensor eta tensor a to omega tensor eta a. And it can be easily checked that this is an isomorphism, right? So the upshot is that any element of E tensor E is a linear combination of elements looking like omega here from here, tensor eta, tensor E. Okay. So I want to extend a map here from here to here. So I will use this isomorphism. So I will just define. So you take any element here. So it's a linear combination of elements like this, right? So it makes sense to define nabla E tensor E on elements like this, because then this is just any element here is a linear combination of this guy. And then I mean, if you just it's easy to write this down, and I mean, once you know what you need, then this definition is obvious. So and then you just check that this is the right connection. So what we did. So again, so this we are in step 1. We assumed a condition on the differential calculus, started with a right connection on E, then I have got a connection on E tensor. Well, I mean so in the next step, we already know how to do the next step, because we already know that from a right connection how to get a left connection. So that was used in the previous method also. So combining this is what we get. So if you assume this condition on the differential calculus and you start with the right connection, you get a left connection on E tensor E whole star. And remember that the metric G is an element of E tensor equal star. So it makes sense to define this. Yeah. So, so this is the second approach. Uh, yeah, I think I should stop now. I don't know how far I could convey the idea, but yeah. So over to you, Shomal. I mean, if there are some questions.
Is there any question? If not, then I think Jyotishman, you can take another 5 minutes. I mean, to
No,
if
actually,
you
I mean,
can't.
so this is my, I mean, this was my target because, yeah, I mean, so of course, I in the slide, I have some other things too, but, uh, yeah, I mean, so this is what I wanted to convey. I mean, how to
Okay.
make sense of this equation.
Mhm. Okay.
So, yeah, I mean, if needed, I can try to repeat some of what I said, but yeah, I, 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 I can, of course, talk about some other things, but maybe, yeah, I have spoken enough. I mean, so, I mean, is there someone who want to know more? I mean, then only I will proceed. Or
So, Professor Ajit Iqbal Singh has some question for you.
yeah, okay,
Okay.
capital sigma symbol, left upper lower script cutting meaning. Okay. Uh, okay. Let's see. Let's see. I think. Oh, oh. Uh, wait. I Yeah. So maybe Professor Singh was asking about this. So yeah, I mean, so I haven't used the Einstein uh, notation, but yeah. So this upper and lower actually comes from Einstein convention, but I haven't used it. Was that the question? Uh, yeah, I mean, Shoma, look,
Yeah.
can you hear
So,
me?
okay. So, is there any other question?
You say,
Yeah, I can hear you.
yeah, you see, when do you decide to have C linear and A linear?
Oh, right. So all the maps that I talked about are C-linear maps, but my connection is not a C-linear
Uh,
map, but my metric is sorry, sorry. I mean, my connection is not is not an A-linear map,
uh,
uh, because I have this extra term,
uh,
but my metric
uh,
is assumed to be only right A linear.
okay.
Yeah.
Mhm. And when you go to the dual system, then you will take left A linear.
No. By the dual, so I always mean the right A linear maps.
Okay. So, no, what I wondered was usually in module theory, if module is right module, then dual is left module.
Right. Yeah. Actually, yeah, I understand what you mean.
Huh.
But since I am starting with a bi-module
Okay. Yes.
in our special case,
Yes. Yes.
so it has got also a right structure,
Right. Okay.
and
Okay.
I'm going to exploit that structure.
Okay. Fine. Thank you. Thank you.
Any other questions?
Can I ask? I mean, what is the reason for right instead of left? Is there some reason for the choice, or there will be dual? There will be equal theory.
Yeah. Uh, I mean the I mean the I mean the theories will be uh, equivalent. So
Okay.
yeah,
Okay.
it's just
Okay.
my convention.
Fine. Thank you. Thank you.
Yeah, sure. No?
Okay, so if there are no more questions, let's thank Professor Jyotishman Bhowmick for the nice talk.